In this video, I'd like to talk about the math question of the day for February 21st, 2023. And with this question, we need to find the inverse of the one-to-one function f of x, which is shown here. And to answer a question like this, you do need to have a very solid understanding of algebra and likely some exposure to pre-calculus, since this can be a little bit advanced, especially dealing with this one-to-one idea for a function. So at this point, go ahead and pause the video, see if you can work through this question on your own. And when you're ready, unpause the video and we can go through this together. Now, assuming that you have at least attempted the problem, we can start working through this. And as always, if you do have a suggestion for a future math question of the day, feel free to leave that suggestion as a comment below. And when dealing with inverse functions, they have many special properties. But one of the main ones, if we were to look at some graph, let's say we have some function that maybe is just a line. It looks, let's say, like that. Then the function that is inverse to this, or we can say this function's inverse, would have the special property that it's a reflection about the line y is equal to x. So let me draw in that line. This is the line y is equal to x. And all inverse functions reflect across this line here. So if we look at the function that is the inverse of the green one, it would look like a mirror image across that line. And I'm not going to draw this perfectly, but you can get a rough idea of what's happening. Let me try that one more time. And the inverse function will always intercept its function on this line y is equal to x. That's where they always cross. And the reason for that is that with inverse functions, we essentially switch x and y and then solve for that other variable. So for instance, right now, this is f of x is equal to 3 over 2x plus 1. We set this equal to y. And to find its inverse, we just switch x and y and then solve for that other variable. Or in other words, we switch for x and y and then resolve it for y. And since this is a rational function, it's going to look different than this linear function. In fact, it would have an asymptote at minus 1/2. That's when the denominator would be equal to 0. And it would look maybe something like this right here. So its inverse function will be a little bit difficult to draw. It will actually look somewhat similar to this, but this function is invertible. And we know it's invertible because it is a one-to-one function. And what this means is that for every x value, there is exactly one y value. And we know that because it's a function. That's the definition of a function. But a one-to-one function means that for every y value, there is exactly one x value that leads to it. So a function that is not one-to-one, let's write that down. So not, let me use symbols, not 1 to 1 would be the function y is equal to x squared. Since if we quickly plotted that, it looks something like that. It's the parabola. Every y value, let's say a y value of 4, has two possible x values that lead to it, namely at x is 2 and x is negative 2. So this function right here is not one-to-one. In fact, it fails what we call the horizontal line test. If we draw a horizontal line at any point, if it passes through the curve at 2 points, then it's not one-to-one. But if it only passes through at 1 point, which it would if this were, say, a cubic function, let me get rid of my line tool there. If it's a cubic function, the horizontal line test would pass. Anywhere you draw a horizontal line, it only passes through once, meaning that the cubic is one-to-one and therefore invertible, but the parabola, the quadratic, is not one-to-one. If we wanted to find its inverse, we would have to restrict the domain and say that x has to be bigger than or equal to 0, essentially cutting off this left half part so that the horizontal line test starts to work. So that's the process. If it's not one-to-one, we have to restrict that domain, but we are assuming this is a one-to-one function. We're told that. So from this information, we can just switch x and y and then actually resolve it for y to find the inverse of that function. And conveniently, there is a nice way to test this at the end. So let's start by switching x and y. So instead of y being here, we now have x. This is 3 over 2y plus 1. And since we need to resolve this for y, we need to get y out of that denominator. So we multiply both sides of the equation by that denominator, that expression, 2y plus 1. And on the right-hand side, it will cancel out. We just get 3. And on the left-hand side, I will first just rewrite this, 2y plus 1 times by x. Since we need to solve for y, we can divide each side by x, so that we get 2y plus 1 is 3 over x. And let's subtract 1 on each side. So we get 2y is 3 over x minus 1. And dividing everything by 2, y is 3 over 2x minus 1/2. And you'll see this is also a rational function where the degree of the denominator is 1, just like it was in the original function. But it's just been shifted around compared to the parent function, y equals 1 over x. But if we did plot both of these, the function and its inverse, we would find that they do have this symmetry about the line y is equal to x. So this new equation here that we solved for y after switching x and y, this is the inverse function. We can call this f inverse of x, where this is not raised to the minus 1 power. This is just the symbol for inverse function. And if you want a way to check this, the approach that I usually take is to plot some random point in this function. And let's just use 0, since that's simple. We pick an x value of 0, and we get 3 over 0 plus 1, which is 3 over 1. So when you plug in 0, you get back 3. But remember with an inverse function that we switch x and y. So in our inverse function, this should go through the point 3, 0. And if it does, then we know we did this correctly. So let's actually plug that in. If we plug in f inverse of 3, we get 3 over 2 times 3, which is 6. We're subtracting half from that. But 3 over 6 is 1/2. 1/2 minus 1/2 is 0. So we got back the point we expected, this point 3, 0, which means we can feel confident that this is in fact the inverse to our given function.